So if you ever run to me in a bar, especially if I'm already 2 beers in, I'm most definitely going to be start ranting about SDFs. You will say, what the fuck is that? Like, what do they know? Do they even know things? And I'm glad you asked. So let's find out. SDF stands for sign distant field. Some other people call them sign distant functions, depends on who you ask, but for the purpose of simplicity, we're going to even forget about the sign part right now, and let's try to figure out what even is a distant field. So a field is basically a space, in this case an arbitrary set of points forming a grid representing the pixels on your screen. So imagine that you have a point on this grid, so what you're going to do is for every grid cell, you're going to try and compute the distance from that cell into the point. And you will ask, like, okay, that's good, but how do I know the distance between 2 points? I'm glad you asked, and if for some reason you forget about your high school trigonometry class, there was this cool chap called Pythagoras that made this known theorem that tells you that for any right triangle, the square of the adjacent side plus the square of the opposite side is equals to the hypotenuse. So with this in mind, what you can do is just solve this equation for the distance and just move the square to the other side into a square root. So basically, in order to know the distance between these 2 points, you just need to get the square root of this side square plus this distance square, and you get your distance. Basically, we plot this onto our grid. You will see that now we have a grid that tells you the distance from every single cell to the closest thing on the screen. In this case, it's just a point. And you say, okay, that's really cool, but you say something about them being signed, and you're right. And instead of a point, we have, like in this case, a shape. Like what you really want to do is not the distance to the center of the shape, but the distance to what we call the isosurface, or in this case, the perimeter of this circle. And the principle here is basically the same. You just know that this side square plus this side square is equals to this side square, but in this case, this side is composed by the sum of this distance plus the radius. So you do basically the same thing. You move the square to the other side as a square root, and then in order to solve for the final distance, you just subtract the radius at the end. And if we plot this, the keen observer will notice that something major has changed, and is that right now the distance has a sign here, the sign distance field. And if you see every cell that has a positive distance, it's outside the surface of our shape. The cells that have 0 under as a distance are right on the isosurface of the shape, and the distance that are negative are inside of our shape. So what we will do is just fill all the negative cells, all the cells with a negative distance, with a color, and then we will have our shape represented on our little screen. And then what happens if you have like multiple shapes? Because in this distance field, you can only store one single distance per each field, per each cell. So the problem with that is that right now you have distance to 2 different shapes. So what you do in this case is just store the minimal distance, because the distance to the entire shape is always the minimal distance between the 2. Especially you can see that if in this case, in this point is at -4 from this surface, but it's at 14 from this surface, and you really want this point to be negative because it's inside the actual shape. The same for all the other points. In here you will just take 4, and in here you will just take the -4 instead of the 14. And if you plot this, again, you will see that all the distances that are positive are outside of the shape of our scene, and all the things that are negative are inside of our shape. And if we do the same of filling them with a color, you could see the 2 shapes are represented. And you say, okay, computer, that's really cool, I guess, whatever the fuck, but what should I even care about that? Like, how is this different from any other approach, classical rendering like rasterization or polygons or triangles or whatever? Well, that's what I plan to show you on a series of videos I'm going to do after this one. But just to let you hang in right here, let me introduce you to a little friend of mine that is called the polynomial smooth minimum. That sounds really scary, and I promise you I'm not going to show you any more math, but it's just to see it as from like a signal processing perspective. When you do a minimum between 2 distances, it's basically like a square wave. The moment it crosses a threshold, it just jumps to the other distance. And the smooth minimum is not exactly like this, but to have an idea on your mind, basically what it's going to do is the things that are really close to a distance are going to maintain that distance, but when they are transitioning from one distance into the other, it's going to do it in a smooth way. And if we plot this, but instead with a regular minimum with the polynomial smooth minimum, you can see here that now the 2 shapes are going to be merged, sort of like if they were made by clay or something like that. And if I just do with the colors, you will see it much more easily that right now, even though this shape is just defined by 2 circles, it creates like this smooth union between them as if they were made of clay. And now I'm going to pull a Todd Howard on you and do 16 times the detail. And if we just animate the positions of this circle over time, bam, how cool is that? Anyway, I hope that this has piqued your interest, and I will see you on the next video. So stay strong, much love, Peace out.